Hamiltonian paths and circuits. So with the Euler paths and circuits, we were talking about going around a graph, only using each edge once. This time we're going to go around a graph only using each point once. So these are actually, I think, easier than the Euler paths and circuits. So Hamiltonian paths and circuits.
Why Hamiltonian?
Because the guy who made it, his name was Hamilton. It's a different Hamilton than the Hamilton method of arranging stuff. So Hamiltonian paths and circuits. Instead of focusing on the edges, we're going to focus on the vertices. Paths and circuits visit every vertex with no repeats. With no repeats. So it's the same thing with a path and a circuit. A path doesn't need to end at the same place, but a circuit does. Different Hamilton than the Hamilton we talked about 2 chapters ago. Think about like a sales guy visiting houses. You what?
There was a cleaning guy who was selling cleaning products.
Okay. And like, I mean, if you're a door-to-door salesperson, you don't want to visit the same house more than once because those old ladies will probably stop that. That's weird. Because those old ladies will chase you away with brooms if you visit the same house more than once. Not around here. They'll probably chase you away with guns. Okay. So there's no nice, neat theorem to determine if a Hamiltonian path or circuit exists, unlike with an Euler path. So let's take a look at an example here. Let's say we have this graph here.
Do they have to be hollow?
Do they have to be what?
Hollow.
What do you mean by hollow?
Do you have to be hollow? Not shaded in.
Well, I mean, all the graphs we've done so far aren't shaded in.
No, the circles.
Oh, no, they don't have to be hollow. I'll shade them in. I was just trying to make them stand out on the overhead. That's all. Okay, so this particular one, if you're taking a look at the degree of the vertices, like this has a degree of 2, this has a degree of 3, so there's 1 with an odd degree. So already there's no Euler circuit. This is a degree of 2, this is a degree of 3, so already there could be an Euler path. Degree of 2, this is a degree of 3. So now there's 3 with an odd degree, so already there cannot be an Euler path. Degree of 2, degree of 3, degree of 4. So no Euler path exists and no Euler circuit exists for this. But that doesn't mean anything about a Hamiltonian path or a Hamiltonian circuit. So because all we're focused on is visiting the vertexes, or the vertices, we're not focused on how many times we visit the edges. So if I wanted to find a Hamiltonian path, I'm just focused on whether or not I visited each vertex. I don't care about the edges. So I'll start out, like, say I want to start at this vertex here. So I'll go over this path to visit this vertex, and then I could go, like, I don't know, down here to this one. I could go 4, 5, 6, 7, 8, and 9. Am I ending at the same place that I started? So did I visit every vertex or did I visit any vertex more than once? Okay. So is this a Hamiltonian path or a Hamiltonian circuit? Path. So this was a Hamiltonian path I went. I went 1, 2, 3, 4, 5, 6, 7, 8, 9. So even though an Euler path and an Euler circuit doesn't exist, a Hamiltonian path would. So if these were like houses laid out on a street, I could go this house, this house, this house. I could visit them in this order and not visit any house more than once. Does that make any sense?
Yeah.
Kind of, sort of. Okay. So there we go. That's a Hamiltonian path and a Hamiltonian circuit. I think these are easier than the Euler paths and circuits because you don't have to worry about like crossing over the edges again. So I think they're easier. Your mileage may vary. Let's take a look at today's assignment. I kind of went a little nuts with the cool designs I made.
Oh. I'm making your handmade ones.
Well, you can't make these like it's.
No, I'm just saying it's like pretty common.
Okay.
Like the worksheets are so overwhelming.
Okay.
If that makes any sense.
All right, so let's take a look here. Number one, you have to find either a Hamiltonian path or a Hamiltonian circuit. I'm okay if you find either one. You just have to tell me like the order in which you visited them. So like you can't just go 1, 2, 3, 4, because I laid these out so that you can't do that. Like if you went 1, 2, 3, you can't just jump from 3 to 4 because there's no edge there. So you have to find a path or a circuit, and then you have to describe what the path or the circuit is over here. So like, find a path or a circuit. So we could go from 1 to 2, from 2 to 3. So you could go 1 to 2 to 3, and then from 3, where could you go? Up to 6, so from 3 to 6. And then from 6, where could you go? You could go down to 4 and then up to 5, or you could go down to 5 and down to 4. It doesn't matter. So let me say I went down to 4 and then over to 5. And then once I'm at 5, I could go back to 1. And if I went back to 1, would that be a path or a circuit? Now if I went, instead of going 5, 4, if I went, I could still go 4, 5. I guess if I went 5, 4, no, I could make it a circuit either way. Cool.
You feel like 1 to 5 to 4 to 6 to 3 to 1, like to 2 and then to 1.
Yeah, that would be a circuit too. So you're just, like the answer here would be laying out the order that you visited the points to make either a path or a circuit. Does that make sense?
Yeah.
Cool. And so that's what you're doing here. So question 1, 2, 3, 4, 5, you're making a path or a circuit. Question number 6, you cannot make a path or a circuit. I want you to explain why. And I gave you a hint as to why you can't make a path or a circuit. So like this little nubbin here that comes out from the main graph, this is called a bridge. And you can't make a path or a circuit on number 6, and it has to do with the bridges. And I just want you to explain why. It doesn't even have to be complete sentences. Just explain to me why you can't make a path or a circuit, a Hamiltonian path or circuit on number 6. And then number 7, another little friendship graph. I want you to make a friendship graph. This time I used Walking Dead characters. So
Coral.
no, there's Carol, and then there's Carl.
No, I know, but Carl. That's how Rick says it. He's all coral.
I know. His accent, because the guy's British, his southern accent is all over the map.
His American, like, I don't know, southern, I guess.
Yeah.
It's pretty decent, though. Like, it's better than his actual British.
Yeah. Well, I mean, that's his, like, he
He's
was
in a movie called